So as I said, it is the variational inference as a topic is classified as advanced topic in data science. There will be, compared to the first, actually compared to the second lecture where I had a lot of equations on the slides. Now, I think that this lecture will surpass that. I will not go into details, but I have to provide some basic background for you to follow what is happening. So again, the last slide as the first one, what we would like to do, there is a field, a special branch in data science where the goal is to find the most suitable model, and it follows the idea of a very old idea called Occam's razor. It is a concept stemming from a British scientist that says that when Mother Nature builds something, the simplest solution is the most probable one. So the idea is, can we somehow use this concept of Occam's razor and to try to find the simplest enough model that is at the same time sufficiently okay in order to fit the observations that we have. So in the concept of electrochemistry, this would mean that, let's say that we have an ice curve that we have measured, and the question is how many time constants or RQ elements, or however you want to call them, are present in that Nyquist curve. So we have, in this case, on this figure, let's say that we have 5 candidate models, and we can fit all of them. It might happen that some of these parameters collapse into the same value, so they don't have any influence whatsoever. Or we can somehow push the optimization process to fit all 5 of them or even more. But the question is, where is the sweet spot? What is the minimum amount of these RQ elements that will provide sufficiently accurate fits? And because we don't have a formalized tool to detect this, we can use some form of advanced statistics to push this through. The second thing that I will be talking about is, can we use the same concept of variational inference to somehow estimate the uncertainty in the ice curves that we are looking at? So the top plot here shows 10 consecutive measurements. We can see that there is some discrepancy here. Yes, there is a gap here. But the goal is, can we exploit the fact that we have probability distribution in each and every of these points that we've measured, and somehow to get this pink haze around the ice curves to say, okay, the solid lines are the ones that we have measured, and the pink haze is the uncertainty of our measurements. So I will not talk a lot about electrochemistry. There will be a lot of theory behind, but the application at the end, I will come back to these slides, will be solely focused on electrochemical impedance spectroscopy. And the final task, what we have today is, let us assume that we have somehow discovered that based on our data, we have 3 RQ elements. Can we estimate their parameters? Yes, we can. That is not a challenging issue. Fitting equivalent circuit models, it's not a problem. But this goes one step further. Can we actually, instead of getting only a crisp value saying that, I don't know, R3 is this many millions, can we assess the distribution function of that, or uncertainty of our estimates, so that we can say that, yeah, this is the mean value plus this much variance, or whatever we're going to see, whatever it is. In such a case, we can show that when we have quite noisy measurements, these PDFs will become wider and wider, which means that we are uncertain in our results, or the uncertainty is bigger, and vice versa. So this is the final task, what we are going to, this is our ultimate goal. And now I have 50 slides between the next one, and when we return and revisit the first 3 slides, full of some strange mathematical concepts that I'm going to try to explain you as gently as and in a more humane way as possible. So we're going to go through 2 topics that are listed here as basics in something, and there is an asterisk. Both topics are actually in the realm of advanced statistical analysis. That's why there is a star on top of them. And then I'm going to show you how you can apply these 2 advanced topics into the field of electrochemistry. This might be a little bit challenging to follow, but I'm going to be talking really, really slowly and try to explain as much as possible in details. So these 50+ slides cover 2 lectures that you can actually check. These are the slides. The first one is quite a new book. It's called Probabilistic Machine Learning Advanced Topics. It's a 2-part series. Each of the books is a little bit above 1,500 pages. So the topics that we are going to cover today is from the second book, that is the advanced topics, and covers chapters 10 to 13. You can open, the books are freely available. They are compiled by a professor from an American university called Kevin Murphy. They have a lot of numerical examples and all the references that are needed to go in a deep dive if someone needs it. And then there is a quite gentle lecture from Princeton University where they cover the concept of variational inference. I will gloss over all of them, but if someone is interested in more detailed background of what is happening, because what I'm going to present today is just a raw, really, really reduced skeleton of what is everything behind. I strongly suggest that you follow these 2 books. The first one might be a little bit challenging because it's really condensed, but the references contained in the first link can help you a lot. So, okay, I'm not sure who is looking at what. To remove this part. Click here, okay. Right. So, what is our goal? Actually, we have 3 goals. We would like to use all this machinery to fit ice curves, or to smooth them and to estimate the uncertainty present there. We would like to use this machinery to fit an equivalent circuit models and solve the problem that I was talking about on the first 2 days, that because they belong to the concept of fractional order systems, we are unable to somehow systematically detect which model is the proper one. And finally, can we apply all of this to estimate the uncertainty in the DRT analysis? So there are a lot of times where I repeated uncertainty, uncertainty, uncertainty. We have two concepts where this uncertainty can stem from. So there is a so-called epistemic. These are general concepts. So it is something that arises because we are unaware what is the true model. So there is some fundamental lack of knowledge when we try to analyze the system, and because of that, there is an uncertainty that we made a mistake when we made some choices. And there is the second one, and this is the most commonly the type of uncertainty that data scientists are playing with, and that is the issues with the parameters values. Are they fixed or are they stochastic? The noise levels in the signals that we measure, and so on. So both of these, in the concept of electrochemistry, both of these concepts are equally present. Because of the complexity of the systems that you work with, it is practically impossible to be certain which model is the correct one. And on top of that, we are dealing with diffusion processes that have inherent randomness in their behavior. And that is why both of these issues are hindering our progress. So, let's go back to basics. There is something called Bayes rule. I'm pretty sure that you've heard of it. You've seen this equation, and it has sorry, 4 components. So there is something called a posterior, there is something called a likelihood, a prior, and an evidence. So let's forget about the evidence at this moment, and let's try to explain what the hell this means in a simple humane form. So imagine that we have a table like here, and I'm turned with my back on the table, and there is a yellow ball on the table somewhere, and I need to guess where the yellow ball is located. And because I'm unable to see the table, I have to guess. So now the first question is, what is my belief where the hell the ball is located? And I can say, okay, the table is flat. I know that the ball is on the table somewhere. That is the things that I'm sure about. So I can say that the ball can be anywhere on the table. That is my prior belief. I can that my prior belief that the probability where the yellow ball is located is uniformly distributed around the table. And then I start doing measurements. I take the red ball and I throw it, and someone or somehow I will get information back that this is the coordinate. Sorry, let's change the color. This is the coordinate where your red ball landed, and it is this much away from the target ball. So I can know that the target ball is somewhere here. So I said, okay, fine. I take another red ball and I throw it again. It will land somewhere here, and it will say, look, now this is this much far away. And I start throwing these red balls over and over and over, and I get these measurements. And over time, I will be able to locate the target ball as close as possible. So where are these concepts coming from? So the prior was the information, my belief that the yellow ball can be anywhere. The things that I was throwing around were my measurements. That is the likelihood where the ball is. And the final thing that I located is the posterior. So based on the measurements that I get, I now changed my prior belief. I now do not believe that the ball is uniformly everywhere, but now I believe that the ball is located here somewhere. So that is the basic rule of Bayes rule in a really simple concept, but this has profound consequences how we do data analysis. And just to change the idea, let us assume that the table is not flat. Let's say that we have a bowl in a shape like this. So let's draw it a little bit better. So a shape like this, and let's say that it is a sticky ball, and I'm throwing a tofu pieces, so a tofu can stick here and maybe slowly drip down. Now my belief, I can say that it is uniformly present everywhere. That I can say that, but it will take me more and more throws to change my belief. It is now safely for me to say that the probability where the ball is located is like this. It's not anymore equally everywhere. So the prior can help us. So this would mean that I will most certainly try to measure it here, because that is where the ball will most probably be. But I can make also a mistake by doing so. For example, if I made a wrong assumption that the table was a bowl, and actually the table was flat, and I took assumption that the prior is like the blue curve, and the ball was actually here, it will take much more measurements to change my prior belief that the ball is towards the end. So this is something what we play around, and this is the concept of Bayes rule. And we're going to use it over and over and over again during these slides, but just imagine that there is the concept of a table and ball, and our measurements is valid. We are going to be doing it in a rather more complicated way, but the same idea holds. So whenever you see this Bayes rule, if you have never felt it in your heart, how it works, this might be helpful to visualize it, what all of these things mean. And then we come to the evidence. And the evidence is probability that the ball, I would say, is there, exists, or whatever. So we should take care. This evidence somehow compiles within itself all possible outcomes. A possible outcome that even the most bizarre scenario that when I threw the ball, the atoms at the ball spontaneously disperse and the ball simply vanishes. Or that the probability that the ball took a path contrary to the second law of thermodynamics and start going upwards, or all these possible bizarrely scenarios are present there. And in most cases, it is impossible for us to estimate this. And you will see that in many examples, because this P of X is more or less constant. It encompasses all probabilities of the state X. You will usually see something like this, that this doesn't exist, and this equality becomes proportional to. So we will come up to this. Just be aware that such a combination can occur. Okay, so as you, the most important thing that in analysis of these problems is something called Monte Carlo approach. Why are we doing it? Because this integral is rather complex one, and we would like to solve it, and it is most probably multidimensional and symbolically for sure intractable. So we somehow would like to solve it. And in order for solving this integral, we need somehow to sample from this distribution. And we don't know it, but we have to take samples of it. So there is there is a field called Monte Carlo analysis. So first, a little background how we came to this name. It was during the Manhattan Project. Von Neumann, and there is one Czech or Polish mathematician, I will remember his name. They were tasked to calculate the amount of nuclear material needed in order to sustain chain reaction. And the idea was, they said, like, we have a core of uranium, and then we can bombard it with one neutron, and then we have several cases. With a probability P1, it will crash with other uranium, and this will produce another neutron, and it will go on. A probability P2 that it will just miss everything. And I can't remember, there was yet another step here, what could have happened, P3, and then stages went around. I'm not a nuclear physicist, but you can find it quite easily. And they said, okay, this is the state of what we are doing. What if we try to simulate? So they start running a simulation, like we said, okay, we took one neutron and run it, and when they come to this point, they throw a coin, and 1/3 of the time they went here. No, 1/3. So P1 percentage, they went to this stage, P2 to here, P3 to here, and they over and over did it a lot of times, and started to count how many times I came here, how many times here, and how many times here. So basically, by simulating this, they were able to calculate the probability, like a histogram, the probability that such a system will end up in one of those stages. And based on that, they empirically calculated how many grams or kilograms of uranium they needed in the start, so in order to have sustained chain reaction. And it was in 1945 one of the first concepts of numerical analysis for solving a physics problem. And it was programmed on the very, very rudimentary, I will say, computer, because for a definition it was. And how they called it, by the uncle of this Czech or Polish mathematician, who was a gambler, and a lot of time of his life he spent it in Monaco, gambling at the Monte Carlo casino, hence the name Monte Carlo. It has nothing to do with gambling or money. It had everything to do with calculating the mass of uranium that was thrown on Japan. But the name sticked, and it's one of the most used algorithms in the world. So the goal is actually what this is solving is, if I have a random variable x distributed with some distribution p over x, and I have some function f of x, what is the mean value of this function? So how are we doing it? We have to solve this integral. This is a definition of expected value, but in order to solve it, I need this p of x. So I sample p of x and solving this as a sum. And I have to do it many times over and over and over again. As many times as I'm doing it, the closer and closer I'm going to get the true result. So one will say, how is this possible? How come that we are sure that these stages in the green graph are actually converging? So the green plot is called Markov chain by a Russian mathematician, and he proved that those under certain circumstances, which are quite broad, these chains converge to a stable distribution. So if we simulate them for a very, very long time, we will get the probability that we enter stage 1, stage 2, and stage 3, and it will converge. So they will be stable. And we can use this concept to sample from any distribution that we think of. Only thing what we have to do is find which Markov chain generates which distribution. And this is where we come to a concept called Markov chain Monte Carlo. I'm going to talk a little bit later on. So now let's get back to the integral that we have below, and our goal is to calculate the value of P. So how can we calculate the value of P? Using Monte Carlo, rather simple. We'll make a square 4 by 4 units, whatever it is, 4 meters, 4 centimeters, whatever, 4 by 4. And we draw a circle within it, and then we turn our backs on and start throwing balls back. And the only thing what we have to do is to be sure that we are throwing balls uniformly. So let us assume that we can throw balls uniformly, and then we throw a gazillion of those balls and calculate how many balls entered the circle versus how many balls entered outside. And if we do this ratio, P will come out. So we actually solve this integral by just throwing balls around. And since we have computers that do not actually complain when you ask them to repeat a certain task million or gazillion times, they are perfect machines to do such a simulations. Only thing that we have to do is just wait for them to finish the cycles. So this is the idea that we're going to use over and over. So the biggest issue that we have is the number of samples that we have to wait. So let us assume that we have the green is the true PDF that we would like to discover, and that we are able to draw samples from it. So the only thing what we have are the blue bars, and we would like somehow to estimate what is the shape of the green line. So we take some samples, let's say in the case A, and then we say, okay, what is the distribution of these bars? And one might argue that the red dots is not a proper one, that this is the distribution that these samples are providing, or maybe this, something like this. Doesn't matter. We can safely say that the bars do not depict the green distribution accurately enough. And then we start sample more and more and more and more. And as these samples reach infinity, in this case, because the distribution is not that problematic, as they reach 100 samples, they start to resemble the true distribution rather close. So that is the main target, what we would like to achieve. Okay, so why was I talking about uniform distribution? Well, when you go on your computer, MATLAB, Python, whatever, regardless of the language, you can take you for sure have a function that will say, give me a random number or distributed by gamma distribution, by normal distribution, but whatever. We do not have algorithms how to sample from these distributions. The only thing that we as a civilization is capable of is sampling uniform numbers from 0 and 1. That is the only thing what we have. Everything else is a mathematical transformation, and it is called inverse transform sampling. This is quite important, and I'm going to explain to you what it means. So this is the only thing what we have on our computers. our computers are capable of producing random number from 0 to 1 almost uniformly. It is so there is computers are static state machines. They have nothing random in them. The only thing that is random is some decay of atoms or whatever, some Mother Nature's stuff. We as a civilization do not have these concepts. So what we do is there is something that is called pseudo-random generators that work in our machines that are actually deterministic machines that have such a huge periods, then statistically speaking, look like a random generators. And that is good enough. And what the only thing what they are capable of doing is generating random numbers from a distribution like this, from 0 to 1, and the area below this is 1. That is the only thing that we are capable of. So what we have to do is somehow convert this distribution into any distribution that we would like to have. And this is something that is done using this inverse transform sampling theorem, which says the following. Let's say that this f of x is a cumulative distribution function of the function that we are looking at. So this one, I guess, in order to follow this notation, this should be, I will change this, big P. So this big P is connected to this small p. And all we have to do is calculate the inverse of this big P and plug in here uniform numbers from 0 to 1, and the result will be the small p. So in such a way, we can generate random numbers from any distribution. And this can be actually easily visualized. So our cumulative distribution function is this here. And imagine that we take a number from here, we go here and then down. This is one sample. Then we take a new number, come here, and this is the second sample. And if we do this over and over and over again, we are going to get our target distribution. And this is how our computers are generating random numbers. So the issue is that we need to know the cumulative distribution function and its inverse. But if we know it, then maybe we can even try to solve this integral. In many cases, we don't even know this, and we would like to sample from that distribution. So now this is really bizarre scenario, what I'm telling you. We are saying that I have a random numbers, there is a distribution, I don't know how this distribution looks like, I want random numbers from that. So how can we do it? Well, this is where these things like Markov chain Monte Carlo stuff come about. I'm going to show you a demo, and you will see this MCMC a lot in data science and in modern machine learning. So this is Markov chain Monte Carlo sampling. Let's see how you can do it. So we would like to sample from this like a croissant like sampling, croissant like distribution. And what is this algorithm is doing is running around, and the endpoint is the sample. And if I try to speed it up, wait, where can I speed it? There was somewhere a speed. Is it? Yeah. And it samples here, and this is how it builds the PDF below. So it's actually building two-dimensional PDF, and we can have different algorithms how it is done. This is called Hamiltonian MC, and then I think that we can. This is the one that is doing really good, Gibbs sampler. So, and you don't have to worry about this. These stuff are implemented just for you to know about. So the algorithm does not know this this shape. It just tries around and calculates the probability that we are in some point and starts to draw only samples that are within this donut. Like we can even go a little bit more bizarre scenarios, something like this, and go nuts. So this is oh wait, yeah. So there are algorithms like this, and it takes quite time to do the samples, but we can do it. And that is why these algorithms are really, really slow. You see, we are using so much time to get only 1 point. It's running still, and took 1 point again and again and again. And there are a lot of algorithms you can play around with them. This one is rather nice. It throws a gazillion samples and it moves it around to find the most probable places where they should end. And on the bottom of the screen, on the left-hand side of the screen, you can see the corresponding distribution that it is implementing. And the final step is rather throws a big punch. So I'm going to wait for it for a second or more. So it slowly converges, and then when it hits the ridge, it will just spread around. It's a really nice effect. Because you see here in the middle, there are no samples. It was impossible to get it, and it will do it. So it's spreading around now. And as you can see, this is rather slow. And when we have to do a million samples, this can take a lot of time, a lot of time. And it's slowly building the, and we have to at some point say, okay, stop, we are satisfied with how this is working. Anyway, so we have tools to do it. They are converging, everything is okay, but they are rather slow. And going back to our presentation, so what we have to do now is the following. So going back to our original problem, it's the Bayes rule that we are trying to solve. And we can solve it using Monte Carlo by sampling from this distribution and solving the equation. But as I showed to you, in multidimensional cases, this can be rather slow. So variational based approaches are doing the following. Say, I would like to know the posterior. I would like to know where my ball is, but I don't know this. I cannot sample from it. It is rather slow. So I will say, look, I don't know how this looks like, but I would like to estimate it. I'm going to assume that there is a distribution, the green one, that is sufficiently close to the one that I want to look at, the blue one, and I'm going to say I'm going to solve my problem using the green distribution. Now this is quite bizarre scenario, because we are saying I would like to approximate the blue plot by the green one, but I don't know how the blue plot looks like. So how am I going to approximate something that I don't know how it looks like? And I have to do it efficiently. And this is a really nice, there is a really nice mathematical trick. I'm going to show it to you. You can actually do it. This is the bizarre stuff. So the goal is, I would like to make the blue and the green as close as possible. I'm going to repeat it over and over. I don't know the blue one, but I want to make the green as close as possible to the unknown blue. And how can I do it? I can do it by solving something I was talking to you about yesterday, this Kuhl-Black-Leiber divergence. So this is a measure that gives us information how two distributions functions are close to each other. So I'm going to measure how similar or how close the green is to the blue one. And again, I don't know the blue one because I knew if I knew it, I don't need anything. I knew my solution. The blue one is my solution. So let's do the tricks. Just to give you a basics. So there are several things about this Kublak library that is peculiar. It is not a measure. This means that if I ask what is the distance between the blue and the green, I will get a number. But if I ask what is the distance between the green and the blue, I will get a different number, generally. This means that it is not a measure. It is different if I go in that direction than if I come back in the other. So that is problematic. No, it's not problematic. That is a property of this. It's not a measure. It's not symmetric. And there is that's why we distinguish two of these, going forward and going backwards. We're going to see what's the difference. There is a second thing that is problematic. Again, this failed. Let me like this. It takes some time to put. There is a second thing that is rather numerically problematic with the Kublak library, is that by its definition, it has a logarithm of the ratio of the two distributions. And we can have places where either Q over Z or P over Z are really small. They tend towards zero, towards the edges here. And this means that this thing will blow up to infinity. So we have to cover these things, but there are two options how we can do it, and they are presented here, and that on this plot. So the first case is assume that my blue distribution has these two modes, and this is the true one. I don't know it, but this is something that I would like. And then I make a wrong assumption, and I say my distribution looks like this. And I would like to fiddle with this green distribution, to squash it, stretch it, and whatever. And I would like to make it as close as possible to the blue one. It is clear that I won't be able to do a proper solution, but the question is, where should I position my green distribution? What kind of result is satisfactory for me? Is this better if I position it here? Or is it better if I position it here? Which one is better, 1 or 2? So the argument here is that number 1 is better. Why? At least I will be able to capture a high probability region, at least one of the high probability regions. Because if I select a solution number 2, then I will position my green distribution on the area where I will not get any blue samples. I should not get, because this area is with low probability, and I'm going to say that the true result has here high probability. And that is why this solution, although wrong, is better than this one. It's more realistic. And that is why Variational Bayes approach uses the version of this Kublak library back and forth that I was talking about, and that is avoiding zero areas. So I'm going to make a mistake here for sure. I will ignore this part. My final result will be wrong, but at least it won't be that bad as this case. So there is like a strange saying in the field of nonlinear analysis that says the following: if we have a linear problem, then we are able to find the true solution of the true problem. But if we have a nonlinear problem, there are two options that we can do. Find the true solution to the wrong problem, or a wrong solution to the true problem. We cannot solve it. So this is the case of finding a true solution of the wrong problem. So our problem is to find two modes. We were able to find correctly only one. So we made a true solution of the wrong problem, but it's better in this scenario. So keep this in mind when we come to a little bit more complicated stuff. So this is the so-called reverse Kullback library that we would like to solve. But we didn't do anything at the moment. We still don't know the blue distribution. We would like to solve this thing, but we don't know the blue one. So regardless, now we have a distribution. We have our cost function that we would like to solve, but we don't know this. So we have to minimize a function that we don't know how it looks like. So let's go on and solve it. Okay, so this is the core equation that you're going to see it everywhere. I'm going to explain it step by step because it is a core one. It might be repulsive when you see it, but it's rather simple. Why is this important? I'm going to go through it, but just to give an idea what we are achieving with this. We were having the Bayes rule like this, proportional to the likelihood times the prior. So the equation on the right is the reduced Bayes rule, and we were solving it usually using Monte Carlo approaches. What this variational approach does is, instead of solving with Monte Carlo, we transfer this problem to a problem of optimization. And this is where machine learning approaches excel at. They're really good at optimizing stuff. So this is really important step. Maybe you don't feel it by heart, but it's really important. Instead of doing statistical analysis, we changed our problem into an optimization problem. Optimization problems are really easy to solve. We can take a computer and tell it, find me the minimum of this function, and it will go around, fiddle, and it will find the minimum, instead of doing all this Monte Carlo simulation. And what we have to minimize? We have to minimize this Kullback library. Again, we said that we don't know this, but let's get rid of it. So let's see what this function does. This function is actually an expected value of this logarithm. And because we have here a logarithm of division, this is changed into minus sign. So we have expectation value of the logarithm of one probability distribution minus the expectation of the other probability distribution. If you are saying like, what does this mean? Let's write this this thing f of x. What does this concept means is the following: integral f of x q of x dx. So whenever you see EQ of something, it is the solution of this integral. We're not solving. We are not going to solve any of these integrals. This is a shorthand notation. So let's go forward. Let's follow this thingy here. What is logarithm of z conditioned by x? Bayes rule. Bayes rule, we write it p z x divided over px is the joint distribution. This is simple Bayes rule. And we do logarithm on both sides. We say here, oh, sorry. I don't know why my pencil is stopped working in the middle. Okay, it has battery. So if we do logarithm on both sides, it will just say logarithm p of x z minus log px, sorry, this one is here, minus px equals log p zx. And this step here is actually what is happening when we go to the next slide. Fine. Then this is changed because we are finding expectation over Q, and I have here logarithm of P of X. So if I write like this, log P of X Q of Z dz, this integral has nothing to do with integration. It goes out, and then this one comes QZ dz, and this is 1. That's why we popped it out of the expectation sign. And then we can go further and further, and we come up to this relation. At this final stage, by doing just simple mathematical arithmetics, the unknown distribution is not present here anymore. Anywhere. It's not present. This part here is the likelihood. It is my measure. If you remember, when I throw the ball, I can always calculate how far I am from the true ball. So this one I can calculate. This one I know. This is something that I assumed. It doesn't say that it is true. And there is this part that is logarithm from all possible expectations, and this is a constant. And I can just ignore it. It is a constant. I cannot do anything about it. Whatever it is, it will stay constant. And what I did is I started by measuring something that I assumed over something that I didn't know. And by doing simple arithmetics, the thing that I didn't know vanished. And when I solve this last relation, I'm actually solving my problem. I will position, and this is the bizarre stuff. So I don't know the blue one. And by doing simple mathematics and using Bayes rule, I will be now able, based on my data, to position the green one as close as possible to the unknown blue one without knowing the blue one. And that is the trick of everything. But I have to know the data, and I have measurements, and we all have measurements. That is the trick about variational Bayes. Why is this important? Because we are not doing sampling with Monte Carlo, which I said it's really, really slow. And instead of doing hardcore statistics, we are doing simple optimization. We are minimizing this last row here. And our function that we are minimizing is this one. Actually, if I'm going to do like this, done. Okay, so we are minimizing this L of this only first portion of the last row, because the last portion is just a constant. And this is called, if you open a book of variational Bayes, this is called evidence lower bound. Why is it called like this? Well, evidence, because it is based on the data that we measured, and it's lower bound because we have this plus sign at the end. Somehow it doesn't like me. Okay, we have this plus sign here. Sorry, I'm going to reset this just to get away with my scribbles. So we have this plus sign at the end. We can never go below this, because this is the evidence. We don't know it. It's a constant, but it's present, and it's pushing us always away from the true solution. The only case where we can find the true solution is if we are able somehow to truly assume the shape of our blue distribution. If we somehow are able to say the blue distribution is in this family, and I will take my green distribution in the same family as the blue one, I will be able to manage it spot on. I will be able to find the true solution of the problem. But this is not always the case. But it's okay. The approximation is enough. So let me show you where all of this mathematical stuff in a comic book style plot. So we would like to find the blue curve, and we have somehow selected the dotted red one. And then we start to fiddle. This dot red one has some parameters. I don't know, its variance, its mean value. We can shift it left and forth. We can maybe explode it, compress it, whatever. But it is all the time probability distribution function. And we start fiddling it with around. How do we fiddle it? We fiddle it by using this equation that was on the previous slide. So what we are actually doing, we started somewhere, and then we went it along. We do some optimization up, down, up. No, sorry, vice versa. This is the true value that we would like. We started somewhere and we fiddled around. The optimization process was working and it was able to come this close. We never matched it. There will be some difference, but we came as close as possible. This border shows us the possible values. When we did some assumption, we said our red dot is of this family. This oval says this is the universe where you can move around. You cannot go outside because then the function doesn't integrate to one. And then we would like to find where can we come as close as possible to the one thing that we would like to get, and that is in the unknown one. And where is this approximation error? Because there is a case that we are unable to find the true solution. We will be always making this gray area error, and this is the thing that we have to live with. If by any chance the true distribution belongs to the universe that we can reach, then we will find the proper solution, spot on. But then this is the question of the design. Okay, so now we are going into a rather nasty part of the presentation. I'm not going to go into details that we see. Okay, 15 minutes. I'm going to just throw around a lot of things that might burden you. Just take them at face value. You should double check them in the references that I gave you. But the idea is the following. The green distribution that we are, let's go back. The green distribution that we are selecting, and that is our choice. We say that you are going to see, on the next hour, I'm going to be selecting a lot of different values for this green distribution, and I'm going to give you guidelines how to select them based on the problems at hand. So we selected this green distribution. What I'm drawing here is rather simple 1D, one-dimensional distributions, because they're easier to be depicted, but they can have a really big parameter set inside. And when we are talking about statistics, whenever you see this like a joint distribution that has multiple parameters, then you know that it's a problem. You cannot split them, you cannot do anything. And they said, like, okay, we are really deep into these problems. Let's not complicate our lives more. Let us assume the following. All the parameters that we have to fiddle around are independent. This is a huge assumption, but since we assumed already so much, we can try to push our luck a little bit more. This simplifies the problem a lot. Instead of doing these joint distributions, we can now flip them as a product. And because we all the time we're doing logarithm, log likelihoods, log, this product becomes a sum, and we can deal sums easily. We can integrate them, split them, do whatever we want. Plus sign is not a problematic one. So whenever you see the thing that they're doing something called like mean field approximation, there is a lot of theory why we can do this, if there were some mathematics in the room, they would have walked out in protest in the way how I explained it. Please don't say this around, that it's easy main field, just take this and multiply it. And that is the final consequence. There is a clear distinction why we are able to do this. Everything explained in the reference. Go and check it if you want. If you don't, trust me, it's like this. Let's go on the next slide. And now we come to something that is called parameter estimation. So we have to, all of these things, what we were doing, we would like to practically apply it for our method, and we would like to estimate parameters of these green functions. There is something that what is called expectation maximization approach. Again, I apologize up front because I'm going to throw all this pile of stuff towards you, and this is approximately half a semester of teaching, condensed on 3 slides. I'm not going through any details. The idea is, can I somehow, I have multiple data points, and I would like to find the parameters of my distribution functions. Can I do it iteratively? So first, I would like to maximize my expectation. So I have some data points, and I would like to make my distributions functions that I've picked out of a hat, of a magician's hat, from my head, throw it out, to maximize the expectation that I see those parameters. And on the next step, I would maximize the likelihood that they come from there. And I do this iteratively over one data point, next. And over a certain time, this algorithm converges, and I will get the true parameters of my PDF. Again, and now I'm telling you, like, trust me, I sent by God the gospel to tell you this. Don't trust me. The process is called expectation maximization. You can find it in the books that I gave them to you. This is in a nutshell, what the hell is this doing? Okay. So this is it. And now the final thing is, we would like to do this expectation maximization in order to solve our loss function. This is the thing that I was deriving with the trick, the algebraic trick, how we are solving this. And this thing, when we are using expectation maximization algorithm to solve our elbow function, in the literature, this is called stochastic variational inference. I'm not going into this. Just remember that these two are connected. And wherever you're going to open a library for doing this kind of analysis, you will see a function SVI. And you will say, oh yeah, this SVI is the thingy that finds these parameters, assuming that the parameters are independent, mean field approximation, and it uses this iterative expectation maximization algorithm to find it. Those 3 things should get into your head. How is it doing it? Feel free to open it and see it. I'm going to, first thing when we start next, or maybe when I finish in 10 minutes, I'm going to open the book just to give you an idea how the hell this works, and just to see the mathematical sausages there in the book and not to be afraid of. So yes, all of this, what I'm going to say now, is in this Murphy book, chapters 10.1 to 10.3. There are only Greek letters on those pages, and everything looks like this. It's written in Greek, but you can understand it if you know some mathematics. It's really, really problematic when you see it on a first glance, and there are a lot of tricks. I'm going to just give you a couple of them, what is happening, and just to get an idea. there is something called amortization, and it is not a concept here, it is a general one. And it says the following. I would like to estimate the likelihood or the variance of my PDF. And my PDF is rather complex, and it has rather complex components, and it takes some time to evaluate it. So can I think of a function that I can calculate really fast that can approximate this? And you can somehow really easily find this function. And then instead of asking your PDF, what's the likelihood, you're asking your function that is quite easy, and you're practically doing so-called amortization. Instead of doing something hard, you're doing something easy, and the solutions are close enough. This is the concept of amortization. And the second thing, what is important, is here we have so-called gradient-based variational inference. If you have any form of optimization, the gradient-based is the following thing. Assume, let's forget now about all of this, and go back to simple gradient descent. If you've heard about it, fine. If you haven't, 3 minutes and you will know more or less everything that you need to know about it without mathematics. Assume the following. We have this function. We don't know it. We have just the data of it. We would like to know where its minimum is. And we would like to get there as fast as possible. Okay? What do? We choose a random point somewhere. Let's say we are here. And we would like to calculate the gradient of this point. And the gradient is the first derivative. And we say, okay, the gradient here is really steep. So I can just jump fast down. I come here and I said, what's the gradient here? And it says, okay, the gradient is not that much. I'm going to jump, but not that much. I'm going to jump a little. And then this gradient slowly levels up. And when the gradient becomes 0, which means the first derivative is 0, I came up to local extreme. And because it's a 0, how much should I jump? 0, I'm there, done. So that's the idea how we are optimizing this. The one thing that that is hidden is I'm drawing this blue lines and saying what is the gradient, I'm not telling you how you can calculate it, but luckily you can actually, these gradients are partial derivative of this over every of these parameters C. And if you, I will open implementation of a library that is doing this. If you've selected a nice form of this green distribution, a Gaussian or something, you can solve this symbolically, and you know the gradients. You just plug in your parameters and you can calculate the gradients. But if you've selected some bizarre form of this Q, you will not be able to solve this derivative symbolically. Then you're going to use Monte Carlo. And this will somehow reduce your process, but at the end, you will be able to get these gradients and easily find the optimal values. This is what it is doing. And the final step, at this point, let me see what's the next presentation. Yeah, I'm going to stop here, and then I'm going to show you the books. The final thing, what I would like to tell you is the following. You should use this trick regardless whether you're doing variational bias or some form of statistics analysis. You should always do this trick, and it's called reparametrization trick. Why is this important? Let me open a new slide so that I can scribble around at it. And it's quite an important stuff that you should use all the time. Assuming that you have the following equation. So I have this Z, and I would like to estimate its parameters. Okay, and I have this data. And I need to estimate the parameters mu and sigma. Because this is random, whenever I take new parameter, my gradients will just jump up and down because I was at one point and now I'm at a different point, up, down, and I wouldn't know where to go. At one point, the gradient will be up, at the next point, the gradient will be down, and my optimization will not go anywhere. It will just be stuck. So what you have to do is rewrite this equation in the following way. You say, look, my mu value is a fixed. That is the thing that I would like to find. And plus there is an error multiplied by the sigma. And I would like to find mu and sigma. They're fixed. But in this case, z is now not a random variable. But if I choose that this e is a standard normal, then z is actually by scaling and translating preserves this distribution. And what I do, I take I do it only once. I take samples from this distribution and they're fixed. And now I can calculate gradients up and down, and this will converge fast. The first equation doesn't converges, the second numerically converges fast. What I did was just a simple reparametrization trick. And this is done over and over again. And it is valid not only for variational Bayes, but whenever you have to fit some stochastically, do this kind of tricks. Okay, now I'm going to pause, but I'm going to show you these chapters just for you to be aware of what is happening. So this is a book. If you turn it around, it will be this big. Just to have an idea. And it's a PDF. I think that I have it even somewhere downloaded. Let's see how fast this is. It's okay. So let's open it. You have supplementary material, everything is there. So this is rather nice book. So 150 megabytes is the PDF. You can buy it. You don't have to. So just to get an idea, there are two kind of table of contents. The brief one, and it ends up at 1,100 pages. So we are focused only on 10, 11, 12, and 13. These are the sections where we would like to go. So this 10.1 and 10.2, just to see how it looks like. So this is what we are talking about. I took some pages from there, and this is how, let me find the thing for expectation maximization gradient. Not. Wait. So it's here. Expectation maximization for variational Bayes for one single Gaussian. And it gives you, these are the results. These are the results, and these are the derivations. And it goes one page, second page, computing the gradients, and it stops here. So you don't have to, you can see it, the derivations are rather simple. You have to go through it. You have everything here plus the gradients and the result, how everything is done. Then you can use this over and over. Everything is there. For numerical implementation, I suggest to use this Pyro. Yes, and I will drop the forum, but pyro.ai, I think it's docs. I'm good. So you see this SVI, stochastic variational inference I was talking about. So you click it. Examples. There are some examples here. Wait, let me see where they were for some tutorial. examples. Yes. So here our introduction, the tutorial, how you solve all of this. And the code is rather simple. So it's just like SVI, my model, and everything. And it's you can just go through this and try these things by hand. You don't have to code anything. I think that everything what I gave you here, you will get an idea when someone says SVI, I know that he was talking about something. Elbow, oh yes, this is the optimization function, yeah, this sausage stuff, okay, and you can go through the code quite easily. You don't, then when you are, so the example here, what he's talking about, it's a rather nice one. It is, wait, linear, this is the one that I would like to, Bayesian regression. So he says, I would like to fit this function, and I don't know it, and I would like to find the distribution of the weights and of the biases. And he's talking about GDPs of countries in Africa. These are the data. And he said, I can draw a linear regression, straight lines, and he can do this. And he says, these are the results. This is the linear regression of non-African nations, a linear regression of African nations. And this is what usually people provide. But if you activate this machinery of variational Bayes, you will get distribution functions of this, or actually how certain are you about this implementations, and then you get stuff like this. And then it goes further, says, look, I did a mistake about which kind of green distribution I took. If I take a better approximation, I will get better results, and so on and so on. And this tutorial goes really, really nice. So you have my slides as a really, 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 really quick and dirty bootstrap. And then you have this book and this implementation. This is actually, this implementation is rather interesting. It was done by Uber. Their goal was, can we somehow predict where the next order will happen? And the goal was, orders are coming randomly around the city. So we have spatial randomization plus time. And they assumed, let's say, that the time is Poisson and some uniform distribution. And based on the data, can we localize where the next call will be? And because it is such a high dimensional problem, there are 3 guys from Princeton that were hired by Uber to do this. They did it, and they implemented all of this and gave it publicly available. This is quite an active project in machine learning. This is quite a lot of use for this kind of stuff. So this is everything that you need to play around with it. In the next lecture, I'm going to show you how you can use all of this machinery in electrochemistry. And for the sake of argument, the problems that they are solving are far, far more complicated than the ones that we have in electrochemistry, but we can use this quite easily.